Welcome back, first-year medical students, to the Med Simplified Hub platform. Today, we're jumping straight into the structural anatomy of long bones. Look, as you're starting your medical journey, mastering the literal framework of the human body is absolutely vital. So today's explainer is really designed to give you that rock-solid foundation. We're going to take a fascinating outside-in journey, starting from the gross macro shape you'll see on the tables in the cadaver lab, right down to the microscopic tissue architecture.
Okay, let's dive into this roadmap. First, we'll look at the ultimate biological lever. Then, the macrostructure covering the shaft and ends. Third, we'll peel back the outer surfaces and membranes. Fourth, we'll explore the inner medullary cavity. And finally, we'll break down the compact and spongy tissues. Section 1. The ultimate biological lever. When you look at long bones, think about the femur in your thigh or the humerus in your arm. I want you to stop seeing them as just static, dead objects. They're actually incredibly dynamic. They are the ultimate biological levers in the human body. Not only do they give us the rigid structural support we literally need just to stand up against gravity, but they also act as the essential levers that our muscles pull against to create every single movement. To truly crush your upcoming anatomy exams, you've got to understand how this lever's specific structure perfectly dictates its biomechanical function.
Section 2. Macrostructure, shaft and ends.
So, if you're holding a long bone in your hand, the most obvious feature is that long tubular middle section, right? We call this the diaphysis, or the shaft. You can kind of think of the diaphysis as the strong, dense central pillar of our biological lever. It has to withstand immense weight and bending forces, which is exactly why it's constructed primarily of incredibly dense, compact bone. It's the rigid core of the whole structure.
But here's the thing. A lever is completely useless if it doesn't connect to anything, and that's where the epiphyses come in. The epiphyses are the wider, expanded ends of the bone. You've got a proximal one, closer to the body's center, and a distal one, further away. These expanded ends exist specifically to form joints with other bones. Because they need to distribute weight across a much wider joint surface, they aren't just solid rock. Instead, they're filled with a lighter, porous material called spongy bone. Let's just take a quick second to directly contrast these two primary structures. On one hand, we have the diaphysis, the long, tubular shaft made of really dense, compact bone, and on the flip side, we have the epiphyses, the wider, expanded ends filled with that spongy bone. Locking this simple comparison into your spatial memory palaces right now is going to serve you incredibly well when you're under pressure trying to orient yourself during a practical exam.
Section 3. Outer surfaces and membranes.
Moving inward from the gross shape, let's peel back the layers. Bone isn't just exposed directly to your surrounding muscles. It actually wears a really tight protective sleeve called the periosteum. This is a fibrous connective tissue membrane that intimately wraps almost the entire outer surface. And it is absolutely crucial for the bone's survival. Why? Because it houses the blood vessels that provide nutrient access, and it plays a massive role in ongoing bone growth and repair.
I said it covers almost the entire outer surface. There is one critical exception. Where the epiphyses actually meet other bones to form joints, the periosteum stops, and instead, the bone is covered by articular cartilage. This is a highly specialized, super smooth, thin layer of hyaline cartilage. It basically acts as the bone's built-in shock absorber, perfectly designed to reduce friction and absorb the really heavy physical shocks that happen when two biological levers are grinding against each other all day. Okay, so we've established the dense outer shell, the fibrous periosteum wrapper, and the smooth articular cartilage at the joints. But here's a really important question for you. What actually lies beneath all this formidable armor? Section 4. The inner medullary cavity. What's really fascinating here is that if you were to cut a cross-section right through the center of the diaphysis, you wouldn't just find solid bone all the way through. No way. Instead, you'd find the medullary cavity. This is a hidden, hollow, tubular space running straight down the inside of the shaft. It basically serves as the central storage vault of our biological lever, and it is completely filled with bone marrow. Now, the contents of this cavity undergo a pretty amazing physiological shift as we age. And let me tell you, this is a highly testable, high-yield fact for your exams. In growing children, this cavity is packed with red marrow, which is literally a bustling factory for active blood cell production. But as we mature into adults, this space transitions. In adults, that cavity becomes largely filled with yellow marrow, essentially repurposing that internal hollow space into a vault for fat storage. And just as the outside of the bone has its periosteum wrapper, the inside needs a lining too. Meet the endosteum. It's a much more delicate membrane that lines the entire interior surface of that medullary cavity. But don't let the word delicate fool you. This internal boundary is incredibly active. It's a primary site where continuous microscopic bone repair and remodeling are happening constantly throughout our entire lives.
Section 5. Compact and spongy tissues. And this brilliantly illustrates the cross-sectional anatomy we've been talking about, organizing it just like how you'd slice through it in the gross lab. Starting superficial, we have that periosteum acting as our outer fibrous membrane for nutrients. Moving into the intermediate layer, boom, we hit the compact bone, that strong, dense outer structural shell. And finally, diving to the deep layer, we find the medullary cavity and the endosteum, providing our hollow marrow storage and that delicate, active lining.
Let's zoom in even further and break down the specific tissue microarchitecture itself. We know the compact bone does the heavy lifting, creating that incredibly dense outer shell. But remember the expanded epiphyses? Inside them, we find the spongy bone. It's this cancellous, honeycomb-like interior that's much lighter. It manages to achieve structural strength without the heavy weight by using a lattice-like network of little struts called trabeculae. And nestled safely in the tiny spaces right between those trabeculae is where you'll find the vital red marrow.
So what ties these macro segments together? It's a crucial junction zone known as the metaphysis. This is the exact area where the long shaft of the diaphysis seamlessly meets the expanded end of the epiphysis. Clinically, this area is massively important because it houses the epiphyseal plate. That's the active growth plate in kids that actually allows bones to lengthen. Once you're done growing, that plate ossifies, leaving behind a visible little structural scar we call the epiphyseal line.
Which brings us to a really crucial point. When that epiphyseal plate ossifies into the epiphyseal line, human vertical growth stops entirely. But the bone itself, it's far from dead. Anatomy is profoundly dynamic. So how does this mature, seemingly solid structure continue to rapidly remodel, repair itself via that endosteum, and actually adapt its dense, compact layers to completely new physical stresses? I'm going to leave that question lingering in your mind, because it's the perfect bridge between the structural anatomy we covered today and the wild physiology lectures you've got coming up next here on the Med Simplified Hub platform. Until next time, keep studying, keep questioning, and keep exploring.